Question 14, total internal reflection has an important applications in fiber optic surgery. A long, narrow optical fiber is used in microsurgery for lessening trauma and the chance of infection and for reducing the healing period. Light within an optical fiber undergoes total internal reflection hundreds and thousands of times without escaping. So that's all really cool. Interesting information. You don't really need to know it to answer the question, but you do need to know the concepts of total internal reflection. And the question is asking for the critical angle of a air-glass interface. So for total internal reflection to occur, you must be going from a more dense to a less dense medium so that the ray bends away from the normal. So in other words, the ray must be in the glass, and then this is going to be air down here, and here comes the ray, and it's gonna, here's the normal, and it's gonna refract to the point that the refracted ray makes a 90-degree angle with the normal. So here's your angle of incidence, here's your angle of refraction, and in this case, your angle of refraction is 90 degrees, and the question is asking, what is your angle of incidence? So what angle of incidence will give you an angle of refraction of 90 degrees? And then, of course, anything above the more than that angle of incidence, and the ray will reflect. And that's how you get total internal reflection. All right, so this is your N1, this is your N2. And we set it up like this. And then it's just a matter of plugging the right numbers into the right place. And even if you make a mistake, you'll know it because you'll get an error on your calculator. So we're solving for sine theta 1, sine theta 2, in other words, the angle of, this is the angle of incidence, this is the angle of refraction, is the sine of 90 degrees, which you should know from math is 1 over, and then you just got to be careful here, and that's why I did this. That's why I put the N1, N2 here. Which goes on the top, which one goes on the bottom? The 1 goes on the top, and the 1.5 goes on the bottom, and then you cross multiply and divide. You don't even have to cross multiply because sine of 90 is 1, so it's just the inverse sine of 1 divided by 1.5, and that's going to spit out an answer of 40.2. That's a typo right there. The answer should be B. It's 40.2 degrees. Number 15, Young's double slit experiment. Monochromatic light is an incident on double slits that are that distance apart. The screen is that far away. The distance between two fifth-order antinodal lines is that. Given the information, the wavelength of light is. Okay, this is a relatively straightforward Young's double slit experiment because they're just asking for wavelength. And they've given you D, and they've given you L, and they've given you X. The only question is, what is N? And you got to read this one carefully. It says the distance between two fifth-order antinodal lines. So your N value is 10. Why is it 10? Let's just do a quick diagram to illustrate that. Here's your central maximum. Here's N equals 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So those are the two fifth-order antinodal lines, and therefore, what's the N value between them? It's 10. All right, that's the only way that you can make a mistake on this question if you got the wrong value of n, because then you're just going to plug them into the formula. And I'll leave you to do that. All the numbers are there, they're straightforward. And you turn out to get an answer of 3.5 times 10 to the negative 8. All right, Young's double slit. The next question is a photoelectric effect question. A burglar alarm is designed to use a photocell with a threshold frequency of 8.35 times 10 to the 14 light with a frequency, so the incident light, so this is F, 1.1 times 10 to the 15, shines on the photocell, resulting in a release of photoelectrons with a kinetic energy of. Okay, we're not going to spend. This is again a straightforward. Here's the formula that I recommend that you memorize for the photoelectric effect. It's conservation of energy question. The maximum EK of the photoelectrons is going to equal the energy of the incident light, incident, minus the work function. A reminder that the work function is the energy that's taken to get the electron off the surface, and then whatever's left will give it kinetic energy. That's why it's a conservation of energy concept. And since they give us the threshold frequency and not the work function, then you have to write it like that. If you really want to, you can factor out the H, and then away you go. And the answer in joules, so we can use 6.63 times 10 to the negative 34 times 1.1 times. Stick all that into your calculator, and you should get 1.76 times 10 to the negative 19. Which is D. Number 17, an incident photon with an energy of 34.7 electron volts collides with an electron. The scattered photon retains 31.5 eV of energy. What is the resultant speed of the electron? Okay, this is a good question. So a photon has this much energy, it hits electron, and then the photon has that much energy. So what happened to the energy that the photon gave up? Well, it gave it to the electron to give it kinetic energy. When we assume that these collisions are elastic, which means all the energy that the photon gives is going to be given to the electron, and therefore we can just go delta E equals. This is one way you can do it. 31.5 minus 34.7, and you subtract those and you get 3.2 eV. You actually get negative, which means, hold on a second, which means that the electron, that's the energy that the photon is giving up, that means the electron has gained that. So if now the electron has gained that has that much energy, we just need to figure out its velocity. Oops. Using EK equals 1/2 mv squared, and we're going to solve that for V. And then plug the numbers in. Just make sure when you're using this formula that the EK is always in joules. So first multiply this by 1.6 times 10 to the negative 19 to get the energy into joules, and then stick it in here, and what do you end up getting in terms of joules? The answer is 5.12 times 10 to the negative 19. That's a 19. And then divided by the mass of the electron, and that's going to give you 1.06 times 10 to the 6th. A. '18 is a knowledge question. De Broglie hypothesized that, well, De Broglie was responsible for, he said that when we discovered that particles could have wave properties, waves, when we discovered that light after the diffraction experiment, the photoelectric effect on the Compton, De Broglie said, is it possible that all particles have, since electrons diffract through a diffraction grating, is it possible that they have wave properties? So he wanted, what De Broglie wanted to do was take this formula here, and this formula here, and calculate the wavelength of something that has mass, right? So we always associated wavelength with this, or more specifically this. We always associated wavelength with the speed of light when you're dealing with electromagnetic radiation. De Broglie hypothesized that, well, can things with mass have a wavelength? And therefore the answer is C. Electrons in motion exhibit wave properties. Okay. 19, the sketch below shows a proton traveling in a straight line through uniform electric and magnetic fields. The electric field exists between the two charged plates is 2.5 centimeters and is maintained with a voltage of 275. If the magnetic field is 2.2 times 10 to the negative 3 teslas, the speed of the proton is, okay, so we've got a proton going in a straight line through perpendicular electric and magnetic fields. So if it's going in a straight line, then that means that the electrostatic force or the electric force must equal the magnetic force. But in this case, they don't give us the electric field strength. They give us the voltage and the distance. Therefore, we have to change E. We have to use this formula here and just substitute in the voltage. And then we're going to solve it for V. So V equals big V, small v, big V. So V equals the voltage divided by the distance. Make sure you change the 2.5 to 0.025. And the magnetic field strength is given to you. Plug those numbers in and you end up getting D. D. All right, let's squeeze in one more. Actually, we won't squeeze in one more. Let's call it there, and then, because then we'll only have to do one more video for the entire thing.